So now we're going to talk a little bit about all that really fun stuff, and by the fun stuff I mean the stuff that's really not fun at all. So things like performance, profiling, and debugging. Basically, trying to figure out why your R code is not working as well as you think it should, and all of that sort of thing. So the learning goals for this session are basically just understanding what are some of the common pitfalls in our performance and our programming, how to identify and measure bottlenecks in CPU performance, and how to identify bottlenecks in memory performance, and how to avoid those kinds of difficulties and issues with CPU and memory performance, and how to debug, some useful tools for how to debug problem code in R. So first, probably the most common pitfall in R performance when you have some sort of R code and it's just taken a lot longer than you think it should to run. The most common reason for that is unnecessarily duplication of objects. I believe Jan showed a little bit of that earlier, where you created some additional copies of objects that you didn't really necessarily intend to create, and the creating those extra objects just blows up your memory and causes R to run really, really slowly when you didn't necessarily expect that to happen. So often, for loops are cited as one of the reasons R is slow, or at least you always hear, don't use for loops in R. And this is partially true, partially not true. It is true that vectorizing your operations in R will usually lead to an increase in performance, but it's not necessarily always true that for loops are always going to be slow in R. You can still write for loops in many situations that are very fast, and usually the actual problem when you write a for loop, usually the actual problem is that somewhere you're accidentally creating extra copies of some data set, some object is being duplicated in your for loop at every iteration or something, and that's what's actually slowing down the code. So a lot of this section will just be learning how to identify when that's going to happen and how to avoid it. So let's start off by just investigating a little bit some of the qualities of performance of those three ways that Sunghang introduced to normalize our data set earlier. So something that you'll notice is in the actual output of this presentation, most of the functions aren't actually run inside the output from the R Markdown document, and that's just because some of these profiling tools don't really play well with the way R Markdown evaluates code, but you can definitely just run them on your own, and I'll show running them from both inside R and also on using a command line version of R, since a couple of them also don't play well with RStudio. Most of them do, but there's one that'll give spurious results in RStudio. So let's go back and just create functions from some of the different ways that Sunghang showed us how we could normalize data way back at the beginning of our course when he was introducing the case study. So to make our life simpler, we'll just grab the data set from our library from our package that we created earlier today, and I'll get the data set from that same package. Then I'm just going to quickly get the logs of the intensities, and so that the rest of this will work. And so here, this first one, I'm just creating a function called normalize loop that uses the for loop approach to normalization. Just going through a for loop, getting the median of the log intensities for each run, getting the global median, and then using a for loop to do the normalization over all of those runs. Now I'm making another function called normalize_vectorized that just does the vectorized version of this, where instead of going through a for loop, it first uses a tapply to get all of the medians, and then uses just a vectorized form of a way of subsetting data in a vectorized form and getting the normalized medians that way. And finally, the last approach, the third approach, is using this merging data frames and aggregate approach. So all of these are just those earlier examples that we saw at the beginning of class when Seung-Hang was presenting the case study and showing different ways of normalizing these data sets. And now we're just going to investigate how fast each of these methods actually run and different ways to improve on that, or why some of them are faster than others. So there are a couple of different tools for profiling CPU performance in R, and usually it's a good first, when you have a chunk of code that's running more slowly than it should, a good first step in trying to improve that code is trying to figure out where the actual source of the slowdown actually is. So we created those functions, but if we just run the function itself and it takes a long time to execute, we don't really know why that's happening or where within that function, what function within that function is creating the slowdown. So the first step is just trying to figure out the actual source of the problem, which function is the source of slow running code. There are a couple different ways to do that. So one is called, there's the MicroBenchmark package, which is really useful for just timing small functions and identifying how long each of these functions takes to execute. So the MicroBenchmark package has a function called MicroBenchmark, which times the execution of code. And this is intended for smaller functions that don't take very long to execute, but which you might execute many, many times. So if you had a chunk of code that took like several minutes or like 2 or 3 hours to execute, you wouldn't want to time that using MicroBenchmark, because MicroBenchmark is intending for smaller snippets of code, and it's really accurate and produces good results because it takes a sample of a bunch of iterations. So it runs it runs a little bit of code like 100 times or so. So you don't want to do that with something that takes 2 hours. You want to break down that bigger chunk of code and time smaller portions of it with MicroBenchmark. It's also there's a built-in function in R called system.time, which can be useful, but MicroBenchmark is going to be a lot more accurate than system.time and is better at timing things that execute very quickly. So when you're timing smaller functions that you may call 100 million times or something, MicroBenchmark is good at telling you how fast that actually is going to run. Because if you have something that takes like 1 microsecond versus 1 nanosecond, you can be really hard using system.time to figure out which one is actually faster and whether something is consistently taking 1 microsecond versus 2 microseconds. But MicroBenchmark will tell you and help illustrate those differences. There's also rprof and summary rprof from the utils package. So it's in the utils package, which comes with your standard installation of R. So rprof and summary rprof will generally be pre-installed for you with any R installation. And these are good functions that basically you run a chunk of R code using this rprof function, and then summary rprof will break down how much time was spent within each function call during that execution of that code, and I'll show you what that looks like in just a little bit. So first, we're going to use MicroBenchmark to benchmark each of these different versions of normalization that we have. So I need to check with Mina about having these packages installed. So first we'll install MicroBenchmark, and now we'll actually execute that. So just to save a little bit time, I'm only going to do 10 iterations for this. The default in MicroBenchmark is it'll run each function you give it 100 times, but if you wanted a bigger sample size, you could tell it to run each thing 1,000 times or whatever. In this case, since I don't want to take too long running this, I'm just going to run them 10 times each. So that gives some results. So when you run MicroBenchmark, you just give it each of the code chunks that you want to run, or in this case, I just gave it, and you just separate them by commas, and it's usually better to if you want to compare different code chunks or compare different functions and compare the timings for those with MicroBenchmark, you generally want to do it in one single call to MicroBenchmark rather than calling, MicroBenchmark on normalized loop and then calling MicroBenchmark on normalized vector, and then calling MicroBenchmark on normalized merge. Because when you call them all at once, it'll randomize the order that it executes all of these so that you'll get more reliable results compared to if you ran MicroBenchmark separately on each of them. And and randomizing that can take care of some things. So like if your function relies on loading some kind of data set, the first time that data set is loaded, that might take longer, and the operating system might do some kind of caching or something. So later when you run that, so the first time you run a function, it might take longer to run than when you run it the second, third, or fourth, or fifth times. And so it's also generally good to benchmark things multiple times because of that. But especially in this case, MicroBenchmark will take care of a little bit of it by randomizing the order that it runs these. So just looking at this, it gives the unit in milliseconds in this case, and we probably primarily want to look at the median, but it'll also give the lower and upper quartiles and the minimum and maximum speed that it took to execute all of these over 10 iterations for each one. So we can see here that the loop version, the for loop version, took significantly longer than all of the other versions. It took 3 times longer than the merge version, and the fastest version was this vectorized approach, which took, it was a lot faster than the other versions. That took only 30, so on average, the vectorized version took only 32 milliseconds versus 1500 milliseconds for the for loop version, or about 500 milliseconds for the merging of data frames version. So we can see that at least for this normalization example, that using the vectorized approach was much faster than the loop version or the merge version. And we'll investigate exactly why that is in a little bit. So one way to do that is with these rprof functions that I mentioned. So rprof is just a function from the utils package. So how it works is you just call rprof once, and then you can either give it a file name that it'll write out its output, or you can just leave it blank, in which case it'll just use a default place to write the output. And then you execute whatever code that you want, and then when you're done profiling, you call rprof with null, and that'll end the profiling. In this case, I've also added an interval, because this interval argument changes how often it does the profiling. So basically what this function is doing is it's going to execute some R code, and at every interval of a certain number of seconds, so in this case every thousandth of a second, it's going to basically sample from the R process to find out what function is being executed and get that sort of information. And in this case, since I'm running functions that don't actually take too long to run, so I'm decreasing the interval of it so we can get more information. So I run those, and then you can do summary rprof, which will give a list with a linked to list with members by.self and by.total. The more useful one is by.self. Just gonna. Oh. So you can see what it looks like down here, rather. So you can see that each of these rows is named for a different function, and then it has the time that it took specifically just inside that function, and the total time it took. So that's and what that means is it's a little confusing, but so if you have so the difference between the self and total times here are, so you see that the normalized loop is the actual function that we called, So that's what basically took up all of the time in terms of execution. And you can see, so the total percent of time is basically all spent in normalized loop. However, normalized loop is calling a lot of other functions within itself. So the time, so that's what the difference between self-time and total time are here. So the total time is how long are actually spent within somewhere within functions that were called from that function. So we spent all of our time somewhere in things that were called from normalized loop, but a smaller proportion of that time was actually spent just going through the different lines of normalized underscore loop. Does that kind of make sense?
So you spent most of the time running stuff in normalized loop and spent about 2.2 whatever seconds calling functions from normalized loop. Right?
Yeah, so almost all of the time, like 99% of the time, it was actually 100%, but the things will be a little bit off because it only samples at certain intervals. But basically all the time was spent somewhere in normalized loop or functions called from normalized loop. But about 82% of the time was actually spent with just within normalized loop and not within the functions that were called from normalized loop. So if normalized loop called some other function that took a much longer time to run, this self percent would be much lower for normalized loop. The total percent would still be 100% basically, but if normalized loop called some other function that took a long time. Actually, I'll show this to you. Norm2 normalized loop. Okay, so norm2 is just a function that calls normalized loop. So now I'm going to do rprof again. Interval. And so now you can see in this case, okay, yeah, so if we organize them by the total time, then we can see that most of the time was spent inside norm2, and most of the time was spent in normalized loop. But since norm2 is just a function and all it does is call normalized loop, when we look by itself, that's dominated just mostly by normalized loop. Where else, because norm2 doesn't really do anything. All it does is call normalized loop. So does that kind of help illustrate the difference there between the self and total thing? So norm2 itself is just a function that calls this other function. So norm2 isn't a source of any sort of slowdown. Normalized loop is the thing that's actually slower in this case, and is calling all of the other functions that are slower. So that is an example of rprof for the normalized loop one. Now let's compare the results with the other ones. Yeah, and so that's why I usually am looking at this the results organized by self, because that's usually gonna be more informative than organizing by the total amount of time spent, because the by-dot, when it's organized by the time spent self in each function, that's gonna be a lot more informative in terms of telling you how long or how slow or how fast that function actually is. So here's the output for the vectorized version. And we can do the same thing for the merge data frames version. And you can see in each of these that the amount of time spent in each of the different functions that they're calling is a little bit different because they're different approaches to normalization. So for example, in the version where we normalize things by merging these data frames and using the aggregate function, a lot of time was spent in just this subsetting data frame and sorting the list. We know that data frame is actually a list, so this was some sort of time spent sorting a data frame, probably. There's a lot of time spent in merge.dataFrame. Conversely, in the vectorized version, all of the operations in it were really fast, so most of the time was actually just spent in the function itself. And lastly, in the loop version, most of the time was spent in a lot of time was spent doing the median, and then in sorting, and then access these data frame accessors. So this can be a little confusing when you're looking at all of these different things that are called at some point to do these different things. So let's look at a simpler example. So who here is familiar with the function seek? So seek is a very simple function, just gives you, lets you create a sequence from some number to some other number. So I'm just going to write a really, really inefficient version of this seek function. And so all I'm doing here is I'm taking a sequence, I'm generating a sequence of integers from some integer to some other integer. And so I'm starting with the first one, and then I'm basically creating this while loop where I go from the first one until I get to the last one, and continually concatenating this out vector that I eventually return. So let's test that. So that seems to work. So how fast do you think this function is going to be? What do you think the performance is going to be like on this function for big sequences? Let's do MicroBenchmark first. So first we'll do seek, and then we'll do mySeek. Actually, this may take a little while, so. Let's try it like this. Okay, so it looks like mySeek took a lot longer than the built-in version that R does. So why is that? Why is this looping version taking so much longer? Does anyone have any guesses? So where do you think, so probably we're making some kind of copies somewhere. So where do you think what line would you say, what's the problematic function within this function? So out is just a vector itself. So I'm doing something to out. Yeah, let's find out. So what's this gonna look like? Yeah, so when we look at the profile, we see most of the time was dominated by just this C function for just concatenating these vectors together. So this is a much simpler example where this is a little bit easier to understand. And we can see right away here that the real source of slowness in this function comes from this C function combining these two vectors. And we'll see exactly why that is and how to track down those kinds of problems. So we'll do that by looking now, turning our focus now to profiling memory performance, which is the real source of why this is taking so long. So before I start on that, is there any questions about MicroBenchmark or rprof? Yes. Mm-hmm. So the question is, when do you actually run this? Like when you're working on a package, when's the best time to do this sort of timing, and do you run it all the time? So I would say these are the sorts of things I would. These aren't like unit tests that I would actually include in a package or anything like that, and I probably wouldn't worry about any sort of optimization when I'm first writing R code or when I'm first putting out a package. But definitely after that work is done and you're trying to figure out ways to improve your existing code and it's actually becoming a problem that things are taking a while to run, that's when I would start timing these things and trying to figure out how to improve performance. Because the great thing about R is that you can get away with writing code that takes a little while, because you can write the code so fast that's usually the hard part about coding. If you were writing this stuff in C or C++, it would take a while. Here you can write an R script that does something right away and go get a cup of coffee while you're waiting for things to run. If you're waiting a day or an hour or something like that for things to run, then you should probably start looking at ways to improve that. So I wouldn't really start trying to optimize until it becomes an actual problem. And at that point, I would start timing these things. And I would start, just by breaking things down into first just trying to identify which functions are actually the source of the slowness, and running these things like rprof on the major functions in my package, like normalize loop or normalize vectorize, and finding what are the sources of the problems. So like in this last case, it was really obvious with this example that this C function for concatenating vectors is the source of why that function is so slow. And if that were a function that we had written, then that would be a time to go to MicroBenchmark and try writing different versions of that function that improve on it, and MicroBenchmark those different versions to see which ones are faster than others and that sort of thing. Okay, any other questions about the MicroBenchmark or rprof? Okay, let's look at memory performance, which is the real culprit in most of the slow R code. So there are several different tools to kind of get a handle on what R is doing with your memory. And the first one is just the simplest, which is just GC from base R, which is a way of manually invoking R's garbage collector. So R manages all of its own memory, and whenever you delete an object from your environment, eventually R will do garbage collection, find out, oh, you're not using this object anymore, and actually free up that memory. And that's what GC invokes. Usually that'll happen automatically, but GC forces garbage collection and then also prints out some useful information about R's memory usage. Of course, the default way that it prints it out is a little bit confusing and difficult to read. So there's actually an easier to read version for knowing how much memory R is using from the prior package. And that's just in memuse. So right now R is using about 205 megabytes of memory. And so memuse from the prior package is just basically a wrapper around this GC function that tidies up the output a little and also simplifies it. There's also the mem-changed function from the prior package, which just tracks the change in memory during the execution of a function. So I could do our mem-change. So say I assign some sort of really large vector, Actually, let's say it's a random, some kind of random vector. So we can see that the memory change after creating that vector is about 8 megabytes. And if I were to remove that object, then we get those 8 megabytes back. And so that can be useful to wrap around some to run some R code and run it within memchange to find out how much memory is gained or lost during the execution of that function. Then there's a function called traceMem, which is also really useful. I'm going to talk a little bit about that more in a minute. But first, let's just look at the memchange on each of these normalization functions that we have. So we should actually run those more than once because the first time it's going to be a little off, and that's just because the first time the first time in this case it'll be a little off just because the garbage collector hasn't necessarily caught up to us and what we're doing, so we'll trust these results a little bit better. So not much actually changes in memory during the course of these, but this is only changing this. But this memchange function is only recording the difference in memory from when you first started the function and versus when you actually finished the function finished executing, and that's not necessarily where the actual problem is going to occur. The problem is going to occur during the course of execution of that function. So let's write a function for finding out how much memory overhead is actually being used in that function. So that by that I mean, so a function can use some additional memory while it's actually running that will eventually be freed before the function actually returns some sort of value, and we want to find out how much the function is actually using during its execution rather than just when it's finished. So I'm going to write a function called memmax, which just gets the maximum amount of memory that was used, and that's just something that is returned by this GC function in the final column. So that tells you the maximum amount of memory that R has used during the current session. And you can see that I'm using these triple colons to kind of gain access to some of PryR's internal functions that haven't been exported. So this is something that it's not necessarily good to do at home, except for your own use. Because if I were to include this code in some kind of package that I then gave to users, this would be really prone to breaking, because PryR doesn't export these functions, so they could be changed whenever, and I wouldn't know anything about it. So this is just a way of gaining access to functions that haven't been exported, and you generally don't want to do it at home, but I'm going to do it for this demonstration. So I'm going to get memmax. Then I'm going to write a function called memoverhead. So when you call GC, it takes an argument reset equals true or false, and that just resets the maximum amount used. So with memoverhead, I want to start off by resetting that maximum amount of memory that has been used. This is some magic that executes the whatever code was given to it. Then at the end, I'm going to get the amount of memory that's in use when the code finishes executing, and then I'm going to find the difference between the maximum amount of memory that was used during the execution and how much memory is in use at the end of the function. So let's try this memory overhead on these functions. I'm going to run them one more time just in case there's anything to clean up. Okay, so here we see that during the actual execution of the function, the for loop version uses an additional 50 megabytes of memory in addition to whatever memory is in use when it finishes executing. The vectorized version uses an additional 23 megabytes of memory in addition to whatever is in use when it finishes. And for the merge version, it uses about 60 megabytes in overhead. So where is that memory overhead coming from, and how can we track what's actually being done there? And so to understand what exactly is going on with that memory overhead and what R is doing in the background, we have to understand a little bit more about R and how it copies objects and when it copies objects. So as I was discussing yesterday, R is a functional programming language, and a common feature of functional programming languages is immutable data. And with that comes this basically this pact with the user that if you give me an object, your version of that object won't be changed. So if I have a function and I'm gonna do something with this data that you give me, I'm gonna do that on my own copy of the data, and your data will be left unchanged. So that's this general idea of why R has this idea of immutability. So most objects in R are immutable, and whenever you try to actually change a value in it, usually it's going to end up creating a copy of that object. So R tracks whether an object has multiple references to it. And by references, I just mean whenever some function or whenever something tries to interact with that object, or whenever that object is assigned to another name or something like that. And we'll see exactly what's going on there in a moment. But we can view the number of, we can view what R is doing there with the refs function from the pry-R package. So I'm just going to create a vector x from 1 to 10. And the pry-R package just has these functions called address and refs. And oh yeah, this is the part that I can't actually execute in RStudio because RStudio. So RStudio, to make this environment browser here work, actually has its own references to all of your objects. So this isn't going to work in RStudio. Okay, so. You're right. Okay, so first we just get the actual the pointer address of where x exists in memory, and then refs in R is actually only going to ever be 0, 1, or 2. R doesn't actually keep track of a true reference count of how many references an object has to it. It just counts whether there's more than 1 or not, whether there's 0, 1, or more than 1. So in this case, 1 means that there's only one name bound to this vector of 1 to 10 at the moment, and that name happens to be x. So right now, there's x only has a refs count of 1. So let's assign something into x. Will these be the same? Will the address be the same, and will the refs be the same? Who thinks the address will be the same? Who thinks the refs will be different? Let's see what happens. So the address has changed. The refs is actually still 1. So what that means happens here, what happened here is x is actually now a brand new object. It happens to be a brand new object that still only has one refs to it, one reference to it, but it has already been copied, as we can see by this new address. So x is actually already a brand new object that happens to still have one refs to it, but it's a new object, so it's already been copied. Now let's assign x to something else. So now y and x are the same thing. So let's first look at x. So is the address of x going to be the same? Is the refs of x going to be 1 or 2? So now the refs for x has increased to 2 because now both x and y are pointing to the same data, to the same point in memory. So if I look at the address and refs of y, is that going to be the same or different from x? So that's going to be the same because right now x and y are pointing to the exact same data and the exact same location in memory. So now let's assign something to y. So what has happened to x? X is the same. What has happened to the address and refs of y? Yep, so now y is a brand new object. So it's at a new location in memory, and its refs count is back to 1 because now y is just its own brand new object.
And once the garbage collector comes along, will the refs drop down from X or no?
No, so that's one of the hitches with R and these refs is that the refs count will never go back down unless it actually creates a whole new object, unless it actually copies the object whole. So all it tracks is whether if there's any references to it, if there's and by that I mean if you have something like in a function and you return it and don't assign it to anything, then the refs will be 0. And so that can be safely garbage collected unless you actually assign it to some variable. So you're normally not going to actually see that. But usually, in most cases, you'll see either 1 or 2. And so 1 just means that there's only one name bound to it. 2 means that at some point in time, we don't know if there's still more than one name bound to it. We don't know if there's still more than one reference to it. But at some point in time, something else has touched that object, has referred to it, has pointed to it, or something. But it never goes back down unless it actually is duplicated and becomes a whole new object. So if it actually kept track of exactly how many references an object had to it, then this duplication mechanism could be a lot more intelligent. Because if it were allowed to decrement and go back to 0, then because right now if it ever increases from 1 to 2, then whenever anything happens to it again, it'll get completely duplicated. If R were smart about it and kept track of that more intelligently, and it was able to go back to 1, then we could modify it again in place without R making duplications of it. However, that also makes it makes the language implementation more complicated, and so that has some additional difficulties on the part of the maintainers of R. But there are other languages with garbage collection that have automatic reference counting like that, and that's how some other languages implement garbage collection. Like I think that's what Objective-C does. But yeah, so that's the reason that it would be nice if R actually kept track of the actual number of references to an object. But that has programmatically that has a lot of difficulties in terms of language implementation. So okay, let's see. So now when we last ended, y, we assigned something to y, so y is a whole new object. And when we last looked at x, it was the same object that it was before, but its refs is now 2. So now let's try to assign something into x again. And x is again a whole new object with the refs of 1. So when exactly does this refs get increased from 1 to 2? This is the important part to try to figure out in terms of how to write code that doesn't create a bunch of extra copies. So let's look at this vector that I call z. So z is just a vector from 1 to 16. It has this address, and its refs count is 1 right now. I haven't done anything to it. Let's do a bunch of stuff to z. So I'm going to give it names. I'm going to change its dim. I'm going to change its dim names. So now z has turned into this matrix with these dim names. So if I look at the address and refs of z after changing all of that stuff into it, is z still going to be the same object, and are its refs still going to be 1 or 2? Who thinks z, the address, will be the same? Who thinks its refs count has increased from 1 to 2? So z is actually just the exact same object in this case. So even though we did all of these changes to z, in this case, z still resides in the same place in memory, and its refs count hasn't actually increased at all. And that's because names, dim, and dim names are all primitive functions. So usually whenever a function does anything to an object, usually that'll increase the refs count. Primitive functions, which are functions that are implemented by base R that immediately go into C code. So primitive functions like names, dim names, and so forth, these don't actually increase the refs count. All other functions do, yes?
So in the example before that, so you change the value of one element of x,
Mm-hmm.
and it's got a different address.
Yes.
What happened to the previous? What happened to this memory which had original address?
Yeah, so the original object will still exist for a little while, but whenever R's garbage collector runs again, it'll see that there's nothing pointing to that memory anymore, and it'll get garbage collected and freed up to be used again.
But does it copy? So does it physically? So the chunk of memory which had the original
Mhm.
address, has it been copied to this new address?
Yes.
Or really?
Yes.
Just by changing one element?
Yes.
Force the whole thing to copy?
Yep.
Oh wow.
In that case, yes. Or at least. You know, in that case, I'm actually not sure exactly how much of the data gets copied there, because it might be the case there that so our objects will have some all these R objects are implemented in C at some level, and they'll have some sort of header to them, and then the actual data. So I'm not actually sure how much of that actual data will have changed, and whether just the header got updated in that case or not. So in that case, I actually can't say 100%. I'd have to check more on that. I'm not sure to what extent it creates a deep versus a shallow copy there. I know that's at some points some of those things in the language have changed. Like it used to be with a data frame, that whenever a data frame got copied like that, it used to be a deep copy. So like the whole data frame got duplicated. And whereas newer versions of R will only copy the columns that have changed. Let's see. So we can see the difference between primitive functions like names and dim names, and other functions like we'll create our own function here called ID. All it does is it just returns the object that was passed to it. So if I look at Z, it has that address and its refs is still 1. I'm just going to do ID on Z. All that's going to do is return the same object. And now let's see what happens to the address and refs. So here, just after running that function, that all it does is it just looks at the data set and returns it. It doesn't even look at it, it just returns it right away. Already, just from running that, the refs count has increased. So that object will get copied the next time anything happens to it. So even if I do another primitive function to it, so we know that so we know that dim is a primitive function, but nonetheless, if I try to change dim again, because the refs has increased just by touching it with our ID function, z will get copied and reside in a new place in memory now, even though dim is a primitive function in this case. So how does all of this apply back to the normalization functions that we were benchmarking earlier? So there's this function that I mentioned called traceMem, and what traceMem does is you give it an object, and traceMem will print out a message whenever that object gets copied. So let's do. Actually, I don't need this anymore. So let's do traceMem on our twin data set. So it starts off just by printing where that data set exists in memory. Now let's do our normalized loop on this twin underscore DIA. So what actually happened here is that data frame got copied at every single iteration of that loop. So that would probably result in a pretty slow function when you're whole scale copying your data set at every iteration of your for loop. Let's compare that to the vectorized version. So that still copies it, but it only copies it twice. And the merge version. That one only ends up copying it twice too. I guess before it was copied three or four times. Anyway, so we can see that the loop version was most likely much slower because of all of this additional copying of the data set that happened. Because within the body of our for loop, when we assign into the data frame like that, all of everything within it, that data frame gets copied. And so that's why going through that for loop, that's why that for loop ends up being so slow. In this case, it's not actually that that for loops are just slow in R. In this case, it's because our for loop happens to copy our data set at each iteration. So that's why that ended up being a lot slower. And after we're done with all that, we want to do untraceMem on the twin data set. Otherwise, it'll keep printing off messages whenever that gets copied, and that'll get annoying after a while because objects get copied a lot. Any questions about all of that? So we talked about these tools, MicroBenchmark and rprof for profiling CPU performance, and these tools, especially traceMem, for profiling memory performance. So if you have slow running code, this traceMem function can be really useful in terms of figuring out when these objects are getting copied, because it can happen really unexpectedly, and it can be hard to figure out where or why that happens otherwise. Yes?
So why was the memory usage by the merge function more than for the loop?
I'm going to guess that's probably because well, you can see that these things were copied from different functions, so that extra memory isn't the amount of memory that is used as overhead isn't all going to be from the copying of the data set. That's only going to be some of it.
So
There's
the functions themselves that were used.
Yeah, so there's going to be
That
some additional overhead just from the other functions themselves, and in that case, so even though this is copied at each iteration of that loop, that doesn't necessarily mean it's going to use a whole lot more memory, because after it gets copied, that copy is going to get cleaned up and freed, and then the next copy is going to get cleaned up and freed. So it's not actually going to use as much memory that it would take to store all of those copies. And so probably the aggregate or the merge functions themselves in this version are doing something that requires some additional overhead. They're doing some kind of processing on the data frame, and whatever processing they're doing on the data frame in order to merge them is taking up some additional overhead as well. Let's see. So any more questions about that, or when objects get copied in R? It's a complicated thing, understanding some of this. Any questions? Okay, so then let's talk a little bit about debugging our code. So who here has written our code and it comes up with some kind of warning or an error and you don't know why? It's happened to me a lot. So what do you usually do when that happens? Anyone? What do you usually do? Yes.
Click through the code line by line, not using the debugger because I tried to learn debugging in Perl and ran away.
What do the rest of you do?
Add a bunch of statements at each line.
Print statements. That's always a good strategy to fall back on. So I'll talk to you a little bit about some other strategies for debugging in R. So there are several functions that are very useful for debugging in R and figuring out where an error occurred. Usually, if something gives me an error, the first thing that I'll do is I'll just print the traceback. And all that does is just prints the stack of functions that were called at the time that an error occurred. So here I just have several functions all calling each other, and eventually one of them gets called that tries to add a character to a number, and that's not allowed, so R throws an error. So when I try to evaluate the first one, I get an error, and usually one of the biggest problems with debugging is just not knowing where something happened. So where did that happen? And so the simplest thing to start off with is just looking at the traceback. So that just prints all of the functions that were called as the error until the part where the error occurred. So I called F, which called G, which called H, which called I, and then something unexpected happened. And so that's just a really simple tool. Sometimes it'll just be obvious to you just from the traceback, oh, this function got called that was expecting something different than what I gave to it, and that's why the problem. Usually you'll have to go more than that, but it's usually a good first step. And in RStudio, you can also get a traceback just from the GUI itself. It'll offer to show you a traceback whenever an error happens. So another useful tool for debugging is this browser function. So the next three of these are going to be more interactive debugging that allows you to step through code until you come to the part where the error occurred. And that allows you to inspect the state of different variables and things like that. So maybe you can find out that some variable became a character when you weren't expecting it to. So the browser command is basically, the browser function is basically just a code way of setting a breakpoint. So you would just put the browser statement somewhere in the code where you want to start debugging it. So in this case, I'm just going to put browser in that I function and call it again. So when R goes to evaluate browser, it enters this debugging mode that allows you to, that basically puts you exactly within the code where browser was called. So if I look, I'm inside this this I function. So there's this D. So if I try to list the variables that exist right now, all I see is D because right now I'm inside this I function. So I can, for example, just print D, see what D is right now. And browser has several different commands that you can do. And RStudio also provides these nice buttons that allow you to step through the code visually if you forget what the commands are. But these are the commands for stepping through the code in the browser if you don't happen to be working from RStudio. So N just executes the next line of code. S means to execute the next line of code, and if it's a function, step into it. So if the next line of code is some sort of function call, you then go inside that function as well. When you do S. F just means to finish the execution of the current loop or function. So if you're inside a for loop, F will finish that for loop, but you'll stay in that debugging mode. C means continue execution and exit the interactive debugging mode. So say you go into a function and you figure out what the problem was, or at least you think you figured out what the problem was. So some variable was a string when it should have been a number. While you're inside the debugger, you could reassign that variable to a number, try continuing execution and see if that fixes it. Of course, you would have to then go and change your actual code to fix the problem, but that would just see if that, for example, to see if you fixed whatever it is temporarily. And Q is just to quit the debugging mode. And all of these have corresponding buttons in RStudio. So I can just hit next to go to the next line of code, and that happens to be where the error occurred there. So browser is a simple way, but sometimes RStudio also provides its own version of it, where you don't have to necessarily put these browsers in manually. This is since this is a Markdown document, I can't show you. But if you had a regular R script, it allows RStudio actually just allows you to set regular breakpoints if you're used to breakpoints coming from some other language or debugger. So okay, I need to save this. So in this case, I should be able to set a breakpoint. Maybe I need I guess I need to source it. Okay, so if you have your project in RStudio, saved in RStudio, then you can set these breakpoints just within visually in RStudio. And so in this case, you have to source your R code from RStudio, and so that's another way of adding these breakpoints and entering the browser without actually changing your code if you're working on your project in RStudio. Another function which basically does almost the same thing is called debug. You call debug on some sort of function that you want to debug, and debug can be really useful if you want to find an error that's occurring in someone else's function or in a package or in a function from some other package, because usually in that case you can't go and edit the code from another package, or at least it would be really inconvenient to try to do that and then actually load it. So you can call debug on any function in R, and then that'll enter the browser whenever that function gets executed. So say, for example, I want to debug print.dataframe. So now, whenever I do execute any code that at some point calls print.dataframe, as soon as print.dataframe is called, I'll go into the browser and go into this debugging mode in within print.dataframe. So if you're trying to investigate an error that's happening in some function or some code that you don't control, debug is a really good, easy way to do that. And then when you're done debugging, you call undebug on that function. And then everything just goes back to working as usual. And the last thing I'll discuss is just another another easy way to do this if you're having trouble figuring out where an error occurred, because sometimes the problem with there's a difficulty in still not knowing exactly where an error occurred, and so that's when options error equals recover becomes really useful. And this will allow you to jump anywhere in the function stack and enter the debugger there. So here, I can just set options error equals recover, and oh wait, I should take the browser back out of these. Okay, so with options error equals recover, whenever an error occurs, it'll print the trace of the function calls that exist, and then you can choose wherever in that stack you want to enter. So I could go into the f function, and now I'm in the f function, or I could go into the I function. Now I'm in I, or in any of the functions that were called. And so that can be a really useful way to explore different levels of the functions that were called and try to figure out where an error occurred from there. Another useful thing is sometimes you get warnings and you're not sure why the warnings happened. And so a simple way of debugging warnings is to use options warn equals 2. That converts warnings into errors, so you can actually use options error equals recover and things like that on warnings. So let's see. So if I do options warn equals 2, and if I try to think of something that'll generate a warning, is that a warning in this code? I don't remember. Can anyone think of something that gives a warning? Well, anyway, so
if you try and do a log transform on 0,
let's see.
Or
Nope.
negative value. I do a lot of log transforms, and I always end up with. Or if you do a transverse on a matrix that doesn't have all numbers. Why does that do it? Well, no, don't warnings only come if you have to do it across more than one state. So if you have a vector,
you have to turn on options that warnings are.
Did I already do? Yeah, I already did that. Well, if you ever have any warnings and you're trying to debug the warnings, you can do options warn equals 2, which converts the warnings into errors, and then you can debug them as errors. And to turn it off, you just set options warn equals 0, which turns them back into warnings, and that's the default behavior.
if you do log 2 of -1:10, it'll give you a warning.
Okay. So, okay, so now that's an error, and now options error recovered wants me to recover, and I can figure out what happened there. So that's how you can debug warnings also.
So is it that like for when you set warnings equal to 2, and then you have the debug mode on, right?
Right now I still have options error equals recover, yes.
Right, sorry, options error.
Oh, and to turn that off, because that can get annoying after a while, you do options error equals null.
So if you set it equal to recover, and that pops up, it's going to pop up because you hit an error.
Yes.
So then when you make a selection, does it re-execute everything and then get back to that point?
No, it just goes. So when you have that set up, basically R will still have the state of everything that had happened up to that point of the error. So you just go straight back into whatever was being executed. Yeah. Oh, and options error equals. You can actually put any function in there. So if I could actually just put error equals browser, if I wanted to jump straight to where the error occurred, rather than being given the choice to jump anywhere in the stack. So then I just when I hit the error, it goes straight into the browser without giving you the choice. Or if you want, you could it does have to be a function. Or if you wanted, you could put print statements there if you are so inclined. So you can do options error equals any function that you want to execute as soon as you find an error. And if you're writing a package and you happen to need to execute some kind of code that has a high likelihood of possibly resulting in an error, but you need to try to execute it anyway, it can be good to wrap those either in a try statement or in a try catch statement so that you can recover a little more elegantly from an error, or at least print out a more useful error message than you might get otherwise. So with try, I can do something that would be an error, and so in this case, it's still printing out the error that happened. But if I had this in somewhere in some other code, this or here, yeah. So in this case, since I'm running it interactively, it's still going to print that out. But if I do silence equals true, then there is no actual error that was generated. Basically, what happened here was the error was suppressed, but we still got the message printed out. Here we're suppressing the message as well. So if I had this running in some code and it caught an error, that code would continue to execute after that error happened. And here I'm just doing the same thing, but suppressing the error message. But a more useful thing to do might be to do try catch. And in that case, you can supply a function that you want to have executed whenever you catch an error. And the reason you might want to do that is so that you can provide a more useful error message or a more useful warning message than whatever the actual error message might have been, since you probably know better what you are trying to do than the code that you are calling.
So in real life, what would you put as the first argument of this try catch?
So in both try and try catch, the first argument is just whatever block of code that you want to execute.
So how would you reference it? Function?
So you can actually wrap it in braces like that. So you could have something like that. And say say I wanted to have some sort of function that tries to execute some code that might give an error, but if there is an error, I want to just say return null or something instead of actually sending an error. And in that case, I could do something like and for yeah. So in this case, I'm trying to execute some code, and when the error happens, instead of actually propagating that error or just stopping execution, instead I just return null. And so arrangements like that can be useful in some cases. Any questions on debugging? Yes.
For the try catch, so whenever you spot an error, you skip that error and you proceed to the code. Is that what it does?
So whenever you get an error, you execute whatever function you have. So you have the first argument to try catch is the code that you actually want to try executing. Then it has several arguments after that. So one of them is error equals, and so if you give error equals some sort of function, that function will be executed.
So the code doesn't break if you enter a try catch, even though there's some statement there, the code still.
Yeah. So basically, it'll basically depend what you put in the error equals. So if you still want to signal an error there, you could still create an error there if you want, or you could just return some other value or do something else. Yeah.
But if you want to return an error, would you have to use stop?
Yeah. So I could instead. Do that if I just wanted to print an error that had a different error.
If you wanted to sort of convert it to a warning, would that be?
So then I could do. There's another one for warning. Yeah. So basically, it has different arguments for error, warning, and so forth. So you can just, if you get a warning, you can do something else if you want. Yeah. I believe so. I'm not sure. I think it might only be might only work for errors. Yeah, because I think that'll only actually it'll only actually need that argument if it encounters some kind of error. So warnings will probably still get warnings. You can't. There is a what should I call it? There is another function called suppress warnings. If you want to run some code that you know will generate warnings, but you know it's safe to do anyway, and then you can run. So you can, if you wanted to do something like that, you can run something with the suppress warnings function. I think it's usually probably not a good idea to do that, but I can think one I've used it before when with the plot function, because with the plot function plot can take a lot of arguments in the ... So you can pass a lot of additional parameters to plot. But if you pass something to plot and plot doesn't know what to do with it, it'll give you a warning. But it's safe to do that anyway. It's not going to actually break anything. So sometimes if you want to plot something and send it parameters that it may not actually know how to use, you could run that in suppress warnings, and it'll plot it without printing out those warnings. So that's one way that I've used that one.
Does suppress warnings change it globally, or just you have to wrap the function for which you like this?
Yeah, it's just around that particular function. Yeah. It doesn't actually change whether they are warnings or not. It just doesn't print them for whatever is executed within suppress warnings. Any more questions? If not, this is all I have prepared for the debugging, profiling, and performance. So thank you. We'll take another half-hour break and reconvene in a half hour to talk about scalability in R. Thank you.